Hi, I'm Anna Finnerty-Haggerty, and this is a Chapter 18 practice problem. Okay, so the question reads, calculate the standard cell potential in delta G cell for the following reaction. So we have solid aluminum and solid iodine going to aqueous aluminum 3 plus and aqueous iodine minus. Alright, so the first thing that you're going to do to find the standard cell potential is to write your half reactions. So our first half reaction is 2 moles of aluminum going to 2 moles of aluminum 3 plus, aqueous. So the first thing we want to balance this equation. Our aluminums are balanced, but our charges are not. So our charge for this side is 0. Our charge for this is 2 times 3 plus, which is positive 6. To balance this out, all we have to do is add 6 electrons. Next, what we're going to do is find out if it's oxidizing or reducing. Here it is oxidizing because the oxidizing means that it's increasing as the reaction goes forward, which is the reducing agent. Okay, so our next half reaction is aluminum. We have 3 moles of aluminum going to 6 moles of aluminum minus. In this, it's balanced. Our iodine is balanced, but our charges are not balanced. 6 times -1 equals -6. And to balance this out, what we do is add 6 electrons here. And this one must be reducing, and therefore the oxidizing agent. And then how we find standard cell potential is by using our equation, which equals cathode minus anode. And our cathode is the reducing agent and the anode is the oxidizing agent. So our cathode value is positive 0.53. Our anode value is negative 1.6, and if you add that together, what you get, or you subtract it really, is 2.19 volts. Now what we're going to do to find delta G of cell is that we're going to use this answer to plug it into our delta G of cell equation. So N is the number of moles of electrons, which is 6. F is Faraday's constant, which is 9.65 times 10 to the 4th. And this is moles, and this is coulombs per mole. And then this value is the value we just calculated, which could also be written in 2.19 joules per coulomb. So now we just plug and chug, and what we get for our equation is that all these things multiplied up together is negative 1268010 joules, and you can convert that to kilojoules by dividing by 1,000, and you get negative 1268 kilojoules. So just to sum up the whole thing is, first we found our 2 half reactions of the whole reaction and found out which one was oxidizing and which one was reducing once we balanced it out. And then what we did, we plugged it into our delta E of cell equation, and the cathode is for the reducing and the anode is for the oxidizing, and we found these values in our chart. Then we subtracted those values and we get the total change in standard cell potential. Then we plugged that value into this known equation, and we just simply multiplied these, canceling out all of the common units to end up with joules. And to convert joules into kilojoules, you just divide by 1,000. And that's what we have. Thanks.